the alternator. We can see, in this case, it's hand turned, going in the same direction, and we have our two slip rings with the brushes. Okay. So we get an EMF that changes polarity every half revolution. So as I was saying just now, we rotate that coil. Okay, so we start here, we're going to rotate it in a clockwise rotation. So she goes down and we have a look, and A is now opposite the south pole. And we can see what's happened is it's a changing magnetic field. She goes up and we now have what is known as the peak. And from there it's going to come down. So this is turning. A is now over there. And on the graph, it's that position there at 0. And then it turns. A now goes from, it's gone from the south pole, it's now going on to the north pole, and we can see how it has changed. So we get our alternating current, positive, positive, and then going into the negative. So positive, negative with one revolution. This here is called a cycle, one cycle. In this country, we have a 50 hertz supply. In other words, we have 50 cycles per second. If we have a look at this, a generator that produces an AC output is called an alternator. And we have a look at this. The waveform is called a sine wave or a sinusoid. That's the peak and the positive, and down here the peak and the negative. From there to there is one cycle, and we're going to be learning about the RMS value, the average value, peak to peak value, and the peak value. Okay, so peak value is also known as the maximum. So it could be V max or A max for a current, or I max for current. So just again, 360 degrees, one cycle. So period is the time it takes for one cycle. If an alternator produces 300 cycles in 6 seconds, calculate the period of the EMF. Solution. So the period, which we put down as time, divided by numbers of cycles. So we have 300 cycles and we have 6 seconds. So time on the top, 6 divided by 300, and we should get 0.02 seconds or 20 milliseconds. Frequency is the rate at which the waveform cycles occur. Frequency is measured in cycles per second. We have 50 cycles per second in this country, and we call that 50 hertz. So frequency, the formula frequency equals the number of cycles divided by the time. So question number 2, if an alternator produces 300 cycles in 6 seconds, calculate the frequency of the EMF. Okay, so frequency equals number of cycles divided by time. Number of cycles, 300, time is 6 seconds, so we have a frequency of 50 cycles, and we call that hertz. The relationship between period and frequency is a reciprocal or inverse. If the period of an AC current is 4 milliseconds, calculate the frequency. So frequency 1 over T, and so 1 divided by 4 times 10 to the minus 3. Using that formula there. So our frequency, 1 divided by the time. The time is 4 milliseconds, 10 to the minus 3. Remember, we have milli, micro, nano, and pico. And they go up in stages of 3. So milli is minus 3, micro is minus 6, nano is minus 9, and pico is minus 12. So 1 divided by 4 times 10 to the minus 3, we get 250 hertz. On to number 4. If the frequency of an AC voltage is 200 hertz, calculate the period. Okay. Remember, the period is the time for one cycle. We have 200 hertz. That means my frequency is 200 cycles per second. So to find the period, in other words, the time for one cycle, what I must do is divide 1 second by 200. And that will give me 0.005 seconds. Okay, now we start going a little deeper again. Peak value. There's your peak value. We have a peak value in the positive and we have a peak value in the negative. Okay. So the maximum value of EMF voltage generated occurs at the 90 degrees and 270 degree, which is the negative point. So that down there is 270 degrees. From the beginning to the end, we have 360 degrees. Instantaneous value. The value of EMF at any point of the cycle is termed the instantaneous value. So any point. So if I said to you, there it is there, and it's 30 degrees or it's 45 degrees, using the formula, you'll be able to work out the value of the voltage. Or if you're given the voltage, you can work out the peak or the angle. Okay. So the value of EMF at any point of the cycle is termed the instantaneous value. This can be calculated as the product of the maximum or peak value. So peak value is what we tend to use, but it is also called the maximum value of EMF. And the sign, I left the E out because I couldn't get the 0 in here if I put it in. So the sign of the angle of rotation, theta. So the angle of rotation is known as theta. That's the symbol there. Okay. So V instantaneous equals V peak or maximum multiplied by the sine theta. Theta is the angle of rotation. The question: a single loop alternator produces an EMF with a peak value of 10 volts. Calculate the instantaneous value of EMF when the loop is at 60 degrees. So we're looking for the instantaneous value. We're using the formula. My peak value multiplied by my sine of the rotating angle of rotation. So my instantaneous voltage is 10 because my peak value is 10. So my peak value, 10, multiplied by the sine of 60 degrees. So sine 60 degrees. 10 times 0.866. So sine 60 degrees is 0.866. Now, all I need to do now to multiply that by 10, I move that 1 decimal to the right. It's getting bigger, so it moves 1 decimal to the right, and I get 8.66 volts. So V instantaneous equals V peak multiplied by the sine theta. Theta is the angle of rotation. Okay, let's have a look at this one. If an alternator produces an instantaneous EMF of 75 volts at 30 degrees, what is the peak value of EMF produced? So if it's 75 volts at 30 degrees, we know that at 90 degrees, it's going to be more than 75 volts. So bear that in mind. So we get hold of our formula. V instantaneous equals V peak multiplied by the sine theta. We're looking for V peak. So V peak is in the right place. I need to move sine theta across. So sine theta goes across to the other side and it goes to the bottom. So my formula, V peak equals V instantaneous divided by sine theta. So that there has to move across. And because it's on top here, it needs to be on the bottom over there. And that's where we have it. And it doesn't matter whether I've got V peak on this side or that side. So V peak equals V instantaneous divided by sine theta. Or I can say V instantaneous divided by sine theta equals V peak. So the instantaneous voltage is 75. The angle is 30. With me? So sine 30, what is that? It is 0.5. So V peak equals 75 volts divided by 0.5, which will virtually actually just double that. So we have our peak voltage being 150 volts. Next one, question 7. At what angles? So now note it's not angle, it's angles. Does a generator produce an instantaneous EMF? Go back to this angles. If we have a look at our sine wave, it goes up and it goes down. So a point there is the same as the point there. So if there's 60 degree or say 60 volts here, on the way down, it will also go past 60 volts. So if we've got 150 volts up there, we've got in between 1 and 150 volts up to there, and when it starts going down, we have between 150 and 1. So at what angles does the generator produce an instantaneous EMF of 17.32 volts if its EMF peak value is 20 volts? Okay, so we're given 17.32 and 20 volts. Let's have a look at the formula. V instantaneous equals V peak multiplied by sine theta. What are we looking for? We're looking for theta, the angles. So sine equals, sine is above the line, it's in the right place. I've got to move V peak. V peak must go to the other side. So it's above the line on this side, it'll go below the line on that side. So sine theta equals V instantaneous, stays in its place, and the V peak goes in underneath. So V instantaneous, 17.32. V peak, 20. So sine theta equals 0.866. That's not my angle. I now have to use the arc sine. Sine to the -1. So if you have a look here, theta equals sine -1 of 0.866. And that gives me 60 degrees. Now we know going up we have 60 degrees and coming down we have 60 degrees. So we have it at 60 degrees and also at 180 degrees minus 60 degrees gives me 120 degrees. So 60 degrees going up, and on the way down 60 degrees from the bottom. The bottom is 180 degrees of the top half, so I get 120 degrees. Average value. Now, this is a little different. A lot of students get tied up with this. And the reason they get tied up with this is when it is turned into DC. But we'll worry about that a little later. So if we were to find the average instantaneous value of EMF over a complete cycle, the result would be 0. This is because 1/2 of the wave is positive and 1/2 is negative, and so they cancel out. So the positive minus the minus and it cancels out. However, we commonly rectify alternating current, we turn it into DC. This can be done mechanically as seen in the DC generator, or can be done electronically. Either method produces only positive half waves of EMF. If we take the average instantaneous value of the DC waveform, we get the effective value of DC EMF. So the effective value of EMF is equivalent to the DC average. So V average is the effective value of VDC obtained when AC is rectified. Now please remember, this AC is rectified, there's no capacitor. It's a pulsating waveform. So let's just look at so from the sine wave, we've gone to the rectified pulsating wave. Okay, there's no capacitor. Okay, so V average is the effective value of DC obtained when VAC is rectified, pulsating. The average value can be found mathematically by multiplying the peak value by 2 divided by pi. This value is 0.637, and so we get a formula: V average equals V peak multiplied by 0.637. You with me there? Okay, now the peak value can be found mathematically by multiplying the average value by by pi divided by 2. This value is 1.57. So we get a formula: V peak equals V average. Do you see? V average here is V peak times 0.637. And this here, V peak, is V average multiplied by 1.57. Question number 8. Find the average value of DC that will be produced from an AC supply with a peak value of 300 volts. So our solution: V average equals V peak multiplied by 0.637. 0.637 V peak multiplied by 0.637. So we have 300 multiplied by 0.637. So our V average equals 191.1 volts. A rectified DC voltage has an average value of 50 volts. Calculate the peak value of the AC supply voltage. Solution: V peak equals V average multiplied by 1.57. So V peak equals 50 multiplied by 1.57, so we have 78.5 volts. The RMS value is the effective value of AC voltage. This means that it is the value of AC voltage that does the equivalent work to an equal value of steady DC voltage. Okay, so let's have a look at this. That's pulsating, and we take it as being steady. It's got a little ripple in it. Use more capacitors and we should get it even more flat, okay? So the difference is that and that. That's a ripple, that is pulsating. And the reason it's pulsating, it's actually switching off, whereas this is not switching off at all. So steady DC voltage. If we were to connect an AC supply with an RMS voltage of 50 volts to a heater element and a DC supply with a constant voltage of 50 volts to an identical heater element, both elements would produce the same amount of heat. So they're referring to DC like that, not DC like that, okay? Now, most common measuring instruments measure the RMS value of voltage or current, and it is this value that is referred to on manufacturers' rating labels. Now, all our meters are calibrated to reflect the RMS value. But in actual fact, the value is higher. How much higher? We'll find out now. So RMS stands for root mean squared and describes a mathematical process for calculating this value. However, there is an easier method, or fortunately, the RMS value can be found by multiplying the peak value by the square root of 2 divided by 2. And this value is 0.707. So we get a formula, VRMS equals the V peak multiplied by 0.707. Also, the peak value can be found by multiplying the RMS value by the square root of 2. This value is 1.414, so we get a formula. V peak equals VRMS multiplied by 1.414. Do we see that? And if I double that, I will get that. So we have VRMS, root mean squared, and that is the voltage that we have coming out at the wall, RMS value. Okay, so we have 230 volts, that is RMS value of 325 volts, and we'll be working that out soon. So let's look at question 10. An AC EMF has an RMS value of 230 volts. Calculate the peak value of voltage. So we're looking for peak. 230 volts coming out at the wall. So V peak equals VRMS multiplied by 1.414. So 230 volts multiplied by 1.414, and we have 325.22 volts. So the voltage at the wall is higher than you realize. Now, calculate the RMS value of an AC voltage with a peak value of 150 volts. VRMS equals V peak multiplied by 0.707. So here we have VRMS, V peak, and 0.707. So we have a peak of 150 volts multiplied by 0.707, and we get 106 volts, 0.05.